Next type of molecules we want to talk about are aldehydes and ketones. So a carbonyl is a functional group where there is an carbon-oxygen double bond. So anytime we see a carbon that's double bonded to an oxygen, that is called a carbonyl. So they show up in a lot of different types of molecules, some small, some slightly bigger, but again, we're always looking at carbon double bonded to oxygen. And so there's a lot of different flavors, a lot of different kind of context we can see this in, but in every single case, we call that functional group a carbonyl. And the carbonyl is a part of a lot of different types of molecules that we will see. Aldehydes are then any molecule that contains a carbonyl group where the carbon is bonded to at least one hydrogen atom. The suffix we're looking for here is al or al. It is a little bit different here than we've seen before. So anytime al, it shows up, that's the front of the word aldehyde. So, but methanal is an aldehyde, ethanal is an aldehyde. And so these would be where we have that carbonyl carbon. So, or a double bond, carbon oxygens right here, there's our carbonyl. And you can see there's always hydrogen that's linked into that, either methanal or ethanal. And again, you can see there are some old-timey names: formaldehyde, acetaldehyde. Those names are really clear, and the word aldehyde shows up in them as to what kind of molecule you're dealing with. But they don't fall. They're more kind of old-timey names that have still stuck around because those are really common things. Formaldehyde is a very common molecule that's used a lot, and so that name has really stuck around as opposed to methanal, which sounds kind of silly. Ketones are then when the carbonyl group is bonded to two carbon atoms. So you'd have, say, your carbonyl. Black is the carbon atom, red is the oxygen atom. And so the carbon atom is bonded to two carbon atoms. So the suffix here is -one, as in ketone. So propanone is a ketone. It's the smallest one. You do have to have 3 carbon atoms to make a ketone. This is oftentimes called acetone, so a very common name. But again, you'll see that same suffix -one showing up to indicate that the molecule is a ketone. When we're writing chemical or condensed structural formulas for these molecules, the carbonyl groups do need to be accounted for, and we write them in particular ways. And basically what it is, we just write the O after the C. So for, say, a ketone, we had, say, the CH3 shows up. Then the CO, we don't write the O as branching. We just write the O as next in line in the condensed formula. But you'll note we can tell that this can't be an ether oxygen because this carbon atom doesn't have anything else that it's bonded to. So it would have to be double bonded to the oxygen. So we do want to be careful when it's CO. We want to parse out that that is going to be a carbonyl for the ketone, and then the CH3 over here. When we have an aldehyde, CH3, CH2, the aldehyde, that carbonyl always has to be on the end of the atom, or end of the molecule, because it's attached to a hydrogen on the other side. That has to be the end of the molecule. And we always write that as CHO in the molecular formula. Or in the condensed formula. The reason we don't write COH is because OH indicates a hydroxyl group. So for an aldehyde, it's always CHO. And an aldehyde is always going to be on the end of the molecule because it has to be bonded to a hydrogen. There's nothing on the other side of that. And so it'll always be kind of CHO hanging off the end of the molecule to indicate an aldehyde. All right, so this can add some complications. We want to take some time to look at interpreting some condensed formulas and make some line angle formulas. So I got 5 condensed formulas. I want to take these and draw some line angles. All right, so we're looking for a line angle formula here, and we're given condensed formulas. So when I want line angle formula, what I really want to focus in on are the non-hydrogen atoms. Right? I'm not going to be indicating the hydrogen atoms in any way. So I just want to look at, I got carbon, 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 oxygen, carbon. Okay, and so those are the only things that I need to indicate here. And so the carbons we know are just going to kind of form my backbone forming lines. So the thing I want to be mindful of is when I start to see things like oxygens in there. I want to parse out, well, what is exactly going on? And basically what I want to see here is that I have a carbon that has no hydrogens with it, followed by an oxygen. And that symbol right there tells me that that's a carbonyl. Okay, that's going to be C double bond O hanging off the top. Whenever I see C, because one of the things I can see is that this carbon atom doesn't have any hydrogens. So it doesn't have any hydrogens attached to it. That means it's forming a lot of bonds to other non-hydrogen atoms, which is going to be the carbons and the oxygen here. So when we go to draw this out, I have 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. So it is, a lot of times when we're counting, we have a tendency to count this as 0. This would be like, 1, 2, 3, 4. But we want to be mindful that it should be the number of carbon atoms, right? So 1, 2, 3, 4, 1, 2, 3, 4. So those are the carbon atoms that I've put in there. And then I just need to include the O, which is going to be a double bond because it's the carbonyl O. And so one of the things we can see is that this carbon atom right here, that number 3, it has a single bond to a carbon, a single bond to a carbon, and a double bond to an O. So 1, 2, 3, 4 bonds. That's why there's no hydrogens attached to it. And so that's why that's CO. When we don't see any hydrogens attached to the carbon and it's just an O after it, that's what indicates we're dealing with a carbonyl. And namely, this is a ketone molecule. So if we instead see something like this, where it's carbon CH3, O, CH3, we can see in this case it's different. It's not just carbon into O, it's carbon with hydrogens into O, into carbon. And so that's where we're going to get this basically O, and then a carbon on the other side. Only one oxygen. And so we can see that there is one carbon that has hydrogens on it, and then an oxygen, then a carbon with hydrogens on it. And that's where we get 1, 2, 3. So we can see the difference is it was carbon without any hydrogens into oxygen. That's a carbonyl. Carbon with the hydrogens into the oxygen. That's an ether. CH3CHO. So again, we have the C, the C's and the O's, but this time we have basically another way we can view oxygens in a condensed formula. When we see this CHO, that leads to not only is it a carbonyl, but you're specifying that it's an aldehyde. So you're going to have a carbonyl where the carbon is bonded to one H. Right, so here it was CH3O, that's ether, or CH2O is ether. CHO, it's also always on the end of the molecule. It's always going to be on the right side of the condensed formula. Aldehydes, it's always hanging off the side, right? The rest of the molecule is over here, but there's always this H hanging off the side of the carbonyl. So when we go to draw the line angle formula, I have 1, 2 carbon atoms. So 1, 2, right? I want to be mindful that start of the line is the first carbon atom, and then just that's double bonded to an oxygen. And so this is the line angle formula. When you're dealing with aldehydes, some people just kind of think this looks awkward, where you have this carbon atom with like a single bond and a double bond sticking out the top. It's not uncommon to see something like this, where you write in the H to signify that it is an aldehyde. You don't have to write the H. This is a totally acceptable line angle formula. It's just you commonly see this. I don't know why people are just a little antsy that there's no H there. It kind of looks a little empty hanging off of here, especially because we're used to seeing carbonyls have the 2 things hanging off the side. So sometimes people put the H just to explicitly show this thing is an aldehyde. That's where it is. All right. Let's take a look at a couple more here. HO, CH2, CH2OH. So this is the 4th way we can see oxygens in one of these molecules. You learn this time the oxygens are next to hydrogens. So those are hydroxyls. And so what we can see is that basically this is HO. And you'll note it's written in that direction with the HO, but it doesn't change what the molecule is. That basically the reason why you write it as HO is because it's just like pointing out that direction from the molecule. And in this case, it's pointing out this side. But either way works. You're conveying the same idea. But you can see there's these 1, 2 carbon atoms right here, 1, 2 carbon atoms right there. And then basically just the OHs hanging off the side. There are hydroxyls on both sides of the molecule. One last one. CH2 double bond, CH, CO, CH3. So if we remember CO, that's carbonyl. So it's going to be C double bonded O with things hanging off a carbon. And so it's 1, 2, 3, 4 carbon atoms that are the backbone of the molecule, and that carbonyl hangs off the side. So 1, 2, 3, 4 of the carbons, right? 1, 2, 3, 4, 1, 2, 3, 4. The carbonyl is on carbon 3. And then we'd want to not forget this double bond is between the first 2 carbon atoms. It doesn't matter, I guess, it doesn't matter what side the double line is on for the double bond, as long as it's along that. I tend to put it on the inside, it's a little more kind of protected. It also doesn't have to end, that's fine. If it does connect, that's fine, just as long. You'll see there's kind of a lot of, when you're writing these, you're kind of writing a lot of them pretty fast. So you're not necessarily concerned with how things touch or how pretty it is in the end. What's more important is what information you're conveying. That's a double bond, that's a double bond, single bond, single bond.
Participation 12.5, question 1. A, identify each highlighted group in the cortisone molecule, and B, state how many of that group are found in a cortisone molecule. So this structure over here is cortisone, the molecule cortisone, and there's 3 groups highlighted. I want you to identify them as part A, and then B, state how many of that group. So there's 3 groups. For each of those groups, how many of that group show up in the molecule? This is the first question on participation 12.5, due Friday, December 5th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, identify each highlighted group in the cortisone molecule. So 1, 2, and 3. What are those? Called, and then how many of each of those are found in one molecule of cortisone. I've highlighted one of them, but there may be others. So how many of them, each of them, are in the molecule?
So when we're looking at aldehydes and ketones, the carbonyl group is polar. And so having a carbonyl group in a molecule does tend to make the molecule polar, but it still only tends to modulate a little bit towards polarity. And say you have a bunch of aldehydes, that one carbonyl group is polar, able to receive hydrogen bonds, would tend to be soluble in water, but it's still only one carbonyl group. There is the rest of the carbons in the hydrocarbon chain that would be potentially nonpolar. And just like we saw with alcohols and other oxygen-containing groups, as the chain of carbon atoms gets longer and longer, we tend to have a more insoluble, a more polar compound that is less soluble in water. So ethanol is the highest one. That's super soluble in water. You can mix as much as you want in water. On the bottom here, octanol totally does not mix with water. No mixing at all for octanol in water. It'd be like oil and margarine, total separation, 2 layers. Won't go too much into the chemistry of carbonyls, but because it is very complicated. But there is, you want to note some very important uses of aldehydes and ketones, and that is that they smell. They have really, really strong smells. And so actually aldehydes correspond to a lot of flavors and sense of spices. And so if you look at the names of some of these, like vanillin, that's vanilla flavoring. Cumin aldehyde is what gives cumin its flavor. Cinnamaldehyde, that's cinnamon. And so aldehydes tend to have these really, really strong smells that tend to correspond to something. Now, in real vanilla, there's a wide variety of molecules that make up the vanilla flavor. So you can make vanillin as a single molecule that replicates that. That's kind of one of the more important components of the vanilla flavor. Same with cinnamon. There's a lot of molecules that make up in a real cinnamon, kind of powdered cinnamon or something like that. But if you want to give, say, cinnamon candy, cinnamaldehyde works just fine. It's important to note they don't all smell good. Formaldehyde is embalming fluid. That's our most simple aldehyde. Very strong smell, very, very unpleasant smell. But aldehydes just have a strong smell. A lot of them are good, and cinnamaldehyde in high doses does not smell good. It is overwhelming, but it's just really strong, really, really strong smells. Our noses are really good at picking up aldehydes. Ketones, kind of to an extent, not as strong. Acetone smells really strongly, but it's not like an overwhelming smell.
Okay, participation 12.5. Got our first question for it in this video. We are halfway through. 2 more videos in this set. See you there.